And I think we are live. Hi, Navneet. Hi, Srikant.
Hello, Kavita. Hey,
Hello.
folks.
Hi, Kavita. Hi, Navneet.
Let's wait for a few more seconds so that people can join in and then we can start. Let us know in the comment section where you guys are joining us from. Hello, Ravi. Hello, Bharat. I think we can start now. So, hello everyone, and welcome to day 3 of the conference. I'm Kavita Joshi, Senior Marketing Specialist at TestMu AI, and I will be your host for this session on AI-powered impact-based testing for faster, safer releases. Good to have you all. I hope you guys are having a great time here and joining up with different sessions. And before we start, we just have few housekeeping items to be noted. You can post your session takeaways on LinkedIn or X, tag us, and use hashtag TestMuConf so that the rest of the community also knows and they can follow the conversation ahead. And also, if you have any questions during or after the session, you can drop them in the Q&A. We'll take them towards the end if time permits. Now, talking about the session, running the whole suite on every change is expensive and slow, and most of these tests have nothing to do with the change. The smart engine uses AI to pick the test that matters for each commit based on code modifications, dependencies, historical results, semantic relationships, and test reliability. And it learns for every cycle. So the question on the table today is, how do you run only the tests that matter and still be confident that you haven't missed the critical defect? Today we have with us Srikant Sahoo and Navneet Goyal. Srikant Sahoo is a staff engineer at UKG specializing in AI, machine learning, and software engineering with expertise in LLMs, data-driven systems, and backend development and cloud. On the other hand, Navneet Goyal is a principal software engineer and senior architect at UKG with 20 plus years of experience in quality engineering, software architecture, resiliency, and DevOps. He has led QE and CI/CD transformations across more than 50 teams and previously worked at Amazon, Oracle, and Adobe. So, guys, please join me in welcoming Srikant and Navneet. Srikant, over to you.
Thank you.
Hello, everyone. I'll start. First of all, good morning and good evening, everybody. Let me start the conversation. So let me start with a very simple question like, what if every code change that you do in your system could tell us, okay, what exactly test cases you need to run to qualify that change, right? Most of us are into the system or have seen into a situation where a developer makes a relatively small change, probably small lines of code of changes into the system, commit the code, and a pipeline triggers. And that adds hundreds or thousands of test cases into your queue to run test cases. And we do it for all the valid reasons to get the confidence. We want to make sure that whatever code changes has been done to the system before they go into the production to our customers, they are qualified well and they are not introducing any regression. But as the application grows, as your the line of code grows into the system, and as your regression suite grows, the cost of getting this or gaining this confidence keep getting more and more expensive, right? So, okay, let me. Okay, sorry, I think I haven't shared my screen yet. Can you guys see the presentation? Sorry about that.
Yes, Navneet. It's visible.
Okay, so today we want to explore a different approach where instead of running all the test cases, we want to take a step back and we want to evaluate the code changes that's the changes in the code that's going to the system to predict what test cases makes more sense to run to qualify that change, right? So can we, instead of running all the test cases, can we intelligently find out the test cases which makes most sense to run against that code change. Right. With that, let's dive in. Uh, Kavita already introduced us, so I won't spend much time here, but I'll simply mention here a couple of things here. The topic, the conversation for today's this title about the AI impact that actually touches the title touches the two key aspects, like intersects the two aspects. One is quality engineering at scale, and second is how can we utilize AI to solve the real world engineering problems, right? With that, so getting to the problem, let's understand the problem first, right? We have seen that in last decade or so, the software delivery has changed drastically. Like our code changes are getting much smaller, our deployments are getting, or our builds are getting more frequent, and our deployments into the production system are getting much more frequent. But over the time, what didn't change is how we are running our test cases. We are still, as as the code is flowing to the system, as more and more commits are going to the system, we are still falling. We are still being very traditional into our regression approach, which is like test execution. We pick up all the test cases and we start running those test cases, right? And as the so that can work for a small scale, but if you take it as a larger scale, as the number of teams grows, like more and more engineers working on a distributed system, when teams are distributed, more and more teams are adding more test cases, more and more teams are adding new code bases into the system, right? So that's where the test execution is not able to keep the pace with how software delivery has been emerging in since last decade. uh, and that's the reason, like, the expectation from developer is always been, it's changing in a altogether different direction. When they commit a code, they don't expect the code, the feedback to be coming in next day. They don't expect the feedback of that changes coming in next few hours. They actually want in minutes, in few minutes, they should be able to find out whether the changes they just promoted, is it good or not, right? And that's a mismatch. That's a mismatch into the expectation. While our deliveries is getting much and much faster, our test execution is slowing us down. It's impacting the overall software deliveries and is getting into the bottleneck state, right? So in today's conversation, we want to come up with or share a practical approach about getting much more intelligent and predictive into your test execution, while we are aware of our risk-based execution as well. Let's take a small example, right?
Navneet, can you
Sorry,
do
yeah.
the full screen slideshow?
Okay, yeah, sorry.
Yes, thanks.
Okay, so let's take a small concrete example, right? Let's say in a team, a developer changed 10 lines of code into one of the service. Nothing usual, it happens all the time. 10 lines of code. As soon as code commits gets added to the system, an automated pipeline gets triggered, or a entire CI/CD pipeline gets triggered, and all of a sudden hundreds or thousand test cases gets added into the queue to get executed, and that's add maybe on a 4+ hours feedback delay into the overall system, right? So that's all the bottleneck about this system. So the question is, see, we can add more compute. We can definitely run all the test cases, but the question is, can we run all the test cases faster? The question is, do we really need to run all the test cases? Because taking back to the same example, like 10 lines of code, 50,000 of test cases, what is the probability? Like, does all test cases, 50,000 test cases, have the same probability of getting affected or impacted by those 10 lines of code? Maybe there are few test cases which are directly impacted with that change. Maybe there are few test cases which are indirectly impacted or associated with that change. But a large portion of test cases probably won't have any impact, negative or positive impact, just because of those line of changes, right? So that comes to the question, like, do we really need to run all test cases when we are almost certain that this change won't have any impact on most of the regression test cases? right? And that's gets to a second point, like, okay, can we intelligently predict which test to run, right? And when we look at the cost of regression, it's actually there are a lot. So the one cost is very simple to understand, like the compute cost. When you are running 50,000 test cases for every build or for a small change, there is an underlying infrastructure. There are test environments, there are test databases, there are test runners. So we all understand there is a huge compute bill associated with each regression, but there is the actual cost of this full regression is actually more than compute, which we, like most of the teams, they probably don't understand. A developer just made a commit into the system. He'll be waiting 4 hours to get the actual feedback. He won't be sitting idle to get the feedback and respond to those feedback. Probably he'll shift to another story, another task, another feature to work on. And after a few hours, once he'll get the feedback, again, he has to do a context switching and get to that original problem, reframe the solution, fix something, and get then again put the changes into the pipeline, right? So that adds a context switch. And when you look at hundreds, thousands of engineers working in hundreds of teams, then the cost becomes exponential. And also, when there are multiple pipelines running in parallel, multiple regression workflows running in parallel, they create pipeline congestion, and that delays the deployment. So while we really want to maintain the release confidence, but that's becoming more and more expensive as the software delivery is emerging, right? So it's a compute problem, but ultimately it's down to the developer productivity problem, right? So the developer productivity or velocity suffer when the quality signals arrive too late into the system. And that gets to our, like, that's where that's what I call it as a regression paradox, right? The teams are forced to make two choices, whether like extreme left or extreme right. So if you'll see on the right, on the left side, the one approach is, okay, you want the confidence, run everything, you'll get the maximum coverage of your regression, you'll get the highest confidence, but the feedback will be slower. There will be huge infrastructure involved, cost involved, and then, as I mentioned, there would be developer productivity hit if you run everything all the time. On the other extreme, okay, you can run fewer test cases, you'll get the faster feedback, your cost will be lower, but how will you get the confidence? Does it not gonna impact your confidence into the system? How do you justify your test selection? Right. So that's the underlying problem we are trying to solve here, where instead of like not simply blindly running the fewer tests, we just want to pick the right test so that it's not going to negatively impact our confidence into the system, right? So we want a confidence which can be explained, which can be justified. Now, test selection is not a new idea. Like, teams have been doing the test selection for like probably many years, right? Even and there are multiple ways to do the test selection. Few teams, they pick test priority or test severity, or they add tags like P0, S0, those kind of different tags. They add those tags into the system so that at the runtime dynamically they can pick the right test cases. Few teams, they maintain the static mapping between the test cases and the component that are associated with that test cases, right? So that's a static mapping. Few teams, they follow the path rule, like which these paths are getting are directly related to these test cases, right? And which is similar to the coverage map. And few teams follow the manual ownership. Okay, this team owns these test cases, this team owns those test cases, and they only run those subset of test cases. Each team run those subset of test cases, which is fine. These all approaches are fine, but at scale, at the confidence level, these problems become stale or obsolete or not, I would say, much modern, right? Because tags, they needs a lot of discipline. You want to make sure that all the test cases getting added into the system are tagged properly. The mapping, the component mapping, as your application grows, as you add more test cases or as you edit test cases, update the test cases, that mapping becomes stale, right? And like manual ownership, like for a small organization, you can maintain the manual ownership. For a large organization, distributed teams, that's become a problem, a challenge, right? So in all the test selection approaches that I mentioned above, the missing ingredient is understanding. Unless we don't know what code change is getting to the system, doing the test selection blindly is like half-cooked recipe, right? So we really need to have a mechanism where we can understand what code change is actually getting to the system. What are the dependencies? What are the direct dependencies and the indirect dependencies affected by that code change? Because sometimes, so if file A imports file B and there are code changes into file A, you know that like, okay, file B is also using file B, so that's a direct correlation. But there are a lot of correlation or dependency, downstream dependencies, which are not very obvious looking at the code base, and that's where it starts creating problem, right? So we need a mechanism, a trustable mechanism, a reliable mechanism to find out which test to run and which should be influencing my decision to either pick a test case or not pick a test case, right? And that's a shift from, and that's once you understand, okay, we need a solution, intelligent solution to pick the test cases. You move your approach from a regression to an intelligent regression, right? So if you only look at what test to run, looking at the test suite, that's not going to work. We need to flip the coin and start looking at the other side, look at the code change first, and then identify if this is the code change, what test cases I need to run, right? So you first look at the code. Now you have to find out if that is the code change, what should be the impact? And you have to look at the direct and different type of impacts, which I'll cover in the next slide. But you have to find out what could be possible impact in my regression suite based on that code change. Now, based on that impact, you identified the test cases. Now you rank the test cases by risk, and then you execute the test case. That subset of the test cases for a faster confidence. So with the smart test execution strategy, the question we ask is which tests are most likely to be affected by this exact change, and that subset of the test case of the suite of the test cases is my subset that I'm going to run. Right? And as I mentioned, like I mentioned about impact. Like now, impact could have multiple, like there could be multiple ways to find out the impact. Like most obvious is the direct impact, right? As I said, you are making changes in a file A, and you know that this component has directly, like these are the test cases directly related to those test cases, this component or this feature or this file path. So I have to execute these test cases. But what about the other different type of impact or indirect dependency? Like there could be a indirect dependency, multi-layer downstream into the system that you don't know, right? There could be a semantic relationship between the like two components or the two file paths in our code base, kind of working on the same behavior, right? So that's a semantic relationship. So you need to also, when you're predicting the test cases, you have to look at the semantic relationship as well. There could be a historical relationship, like whenever I make change in component A, these are the test cases which usually get impacted or get failed or start showing a different behavior. So you have to look at the historical test execution pattern as well, right? Another thing is critical path, right? Not a small change into a high priority uh, component like payment or authentication is much more crucial and deserve much more regression than a similar type of code change into relatively not that important component. So you can't really make a decision looking at all things when you are, and you can't ignore the priority list like of that component in your overall application. So all these different signals, when you combine together, that's where we get to our solution about AI-powered impact-based testing. Uh, Now I'll hand it over to Srikanta to cover the next part of this presentation about this tool.
Thank you, Navneet. So far, we have seen why traditional regression testing struggles at scale and why impact is much broader than simply looking at direct dependency. So now I will take you through how we actually solve that problem using AI powered impact based testing. The core idea is very simple. Instead of running the complete regression suite, we identify the test most likely to be impacted by a specific code change. We combined more than 20 signals to make this selection intelligently and change aware. The objective is faster feedback while still maintaining confidence in the release. Most importantly, AI recommends the test, but engineering policy, the risk control still govern what finally we got executed. Next slide. Uh, uh, UIFA, the UIFA, it stands for Unified Impact Fusion Algorithm. This is the main algorithm what actually used to develop this system. It's combine of multiple type of evidence before we selecting a test. Here we categorize 6 type of categorization there. There is a semantic, structural, historical, quality, dynamic, as well as the machine learning part. In in the structural part, you can see that there is a dependency analysis. So, what is dependency analysis? Actually, it's identify which modules, services, or components depends on the change of the code. It's help to reveal the both direct and the transitive impact path. The import analysis is that finds the file that directly import, reference, or consume the changed class, module, or function.
Uh,
uh, the-
Sorry to interrupt, guys. I think there is some voice issue from your end. Can you just mute? Yes. I
yes,
think it's better now.
yes,
Sorry to interrupt, guys. Go
yes.
ahead.
Now let's change the slide. uh, Yes. Now we go for the call graph. What is call graph? Call graph is the trace function and method calls to understand which execution path may reach or be affected by the change code. So next we have in the semantic, in the structural, we have the package coupling. The package coupling is measuring how strongly package or module interact through the call, share the interface, data model, or cross module dependency. That is called a file proximity. Use the structural closeness such as the same file, folder, package, or module as a supportive relevant signal. Uh, uh, Moreover, we can tell that the structural signal tell us what part of the system are technically connected to the change. Now we go for the semantic part. The semantic part, we have the semantic similarities. Semantic similarities is that compare the business and the functional meaning of the change with the intent of candidate of test, often using the embedding or language model. If we take an example, if there is a word called bank, the if I'm going to bank to withdraw some money, the bank is different and river bank is different. If we search for only bank, it's referred to both the river bank and the bank where actually I want to get some money. But if my intent is to go to bank, the intention is not clear in that. So in semantic similarity we get that. Next, we have to go for the code similarity. In code similarity, we find the implementation patterns, identifier, APIs, code structure that resemble the change code. And that is a path similarities. In path similarities, we uses the repository path, folder names, and the semantic information to detect relatives domains, feature, or component. Now we have the metadata match. What the metadata is? Normally, whenever we write some test cases, we write something that this is a regression test case or some data we feel there. That's actually metadata also we capture here, like matches the attribute such as the product, component, feature, the repository, tags, label, platform, workflow, or test type. So moreover, we can say that semantic signal help us understand what the change is about, not just where it is located. Now we go for the historical one. Historical one is there is a historical code change. Actually, we learn which code and test frequently change together across prior commit and pull request. Means we capture all the historical test run in our database, so we can do that. After we go for the failure history. In failure history, look at which test previously failed for the same or the similar code changes, while distinguish real defect from flaky or infrastructure failure. Now we have the test recency. We weight the fresher historical evidence more stronger than very old evidence, usually with time decay rather than the hard exclusion. In the historical, we have test frequency, measuring how much execution history exists for a test, and therefore how confident we can be in historical patterns. Moreover, you can tell that historical signal helps the system learn from what actually happened before. In quality part, we go for the trust score signals. Trust score signal is combinations of supporting evidence into an overall confidence level for a recommended test or a test set. Low confidence can trigger a broader selection or fallback. uh, Next, we go for another signal called coverage overlap. Coverage overlap is that check whether selected test collectively cover the impact area while avoiding excessive redundancy among near duplicate tests. Then we have the explainability. Explainability provides clear reason for selection, such as dependency match, semantic relevance, the historical failures, or the component alignment. Then we have the adoption metrics. Adoption metrics is actually we directly get the feedback from the user, means the developer using our system, they can give the feedback. That's actually the adoption metrics. Then in dynamic, it is a very important things, that in dynamic part we have the change type. We classify the nature of the change. If we get a build, if what type of changes is this? Is it bug fix? It's a feature, it's a refactor, it's a configurational dependency upgrade, database change, API contract change, or test only change. Different change type can require different test breadth. Then we have in dynamic the risk score. We score the risk, means we estimate the potential, the blast radius using factors such as file change, critical component touch, dependency depth, complexity, the production sensitivity, and historical defect patterns. Higher risk should broaden or strengthen test selection. Then we have the priority score. We rank all the candidate test case using our impact, relevance plus urgency and business criticality. So the most valuable test run first actually most valuable tests should definitely in our impact list. So dynamic signal adapt the decision to the risk type and urgency of the change happen right now. Then we have the ML model. We have two ML model used here. One is SGT and another is LightGBM. For every execution happen, we use the SGT model to feature engineering all the signals to fine tune it. And for every bi-weekly, we run the other model to do that, because SGD is very good for the linear data, but the LightGBM is very good for the non-linear data. That's why we pick this. So what actually we learn here, whenever a code change, we first go for check the structural, what is actually connected. Then we go for the semantic, what is actually related. Then we go for the historical, what is this happened before. Or then we go for check the quality, can we trust it. And then finally we analyze the risk and urgency of that change. Then we rank the impact test here. So this is our main algorithm we use inside our engine. Next page. Yes. So considering a simple example, this is the real world example. If we change the password length validation inside the authentication services, so traditionally what happened? Traditionally, it could trigger 1,000 of authentication related regression test case. Instead of, the engine took at direct dependency, semantic relationship, and previous failure and test reliability. It then rank the candidate test and select the one carrying the strongest evidence of impact. So if you get the strongest evidence of impact, only we just run that test case. Next slide, please. Here you can see that one of the most important aspect of our approach is there is one test case, the test password validation. We actually give all the signal have the value 0 to 1, the range is, and after that we weighted some, and finally the impact score is in between 0 and 1. You can see that here the semantic similarity is 0.92, the dependency match is 1, the historical match is 0.85, and the trust score is 0.90, and ML ranking is 0.88. So after the weighted calculation, we give some weight for everything. After the final score of this test case is final impact score for particular changes what we did, that 0.91%. So next. You can see that we have if in our total regression we have 4 type of test case. The test 1, test A, test B, test C, and test D. You can see that for test A we have the impact score is 0.94. For test B we have the impact score of 0.82, and the test C have 0.77, and test D have 0.12. Here actually we define a threshold, and is threshold is defined by the team. So if my threshold is 0.50, so we only select the 3 test cases A, B, C, and we not select the test D as its threshold is less than the less than actually what we define that threshold. So here you can see that the AI is picked only 3 test cases from this. So so ranking whenever actually all the test cases are done the ranking and find out the data here, so we can get the 3 test cases. Next slide, please. Yes, one the important principle is that we don't replace the existing CI/CD ecosystem. What the current engineering team is using, we don't actually replace anything. That we just add or augment it. Uh, Maybe in your Jenkins, in your GitHub Action or GitLab, continue to trigger the pipeline, but before test execution, it call the impact analysis services. The UFA engine analyzed the changes and returned the ranked impact test along with confidence and explanation. This make adoption actually easier because team can introduce the intelligence without redesigning their entire delivery pipeline. Next. Uh, to develop this in at the application layer, we use the FastAPI and Python to expose the impact analysis services. BGM3 provides the semantic embedding, while LightGBM and SGD support machine learning based ranking. PostgreSQL with pgvector store the structural data, and vector representation with Redis support the first access. Uh, the important point is that this technology are implementation choice. The architecture itself is technology independent. Next. Uh, the system continuous learning from every code change and test execution. We ingest the outcome, extract the new signal, update the ranking, predict the future impact, execute the test, and update the trust. Initially, a structural and semantic signal may dominate. Over the time, the historical evidence become increasingly valuable. However, the learning is controlled. We also account for flaky test, environmental failure, drift, and other noisy signal. For an example, that what is ingest results? Ingest result. Every execution. Every execution completion of execution, we ingest all the result to our engine. So what happened, we know that which test case is failing, which test case is failing for what, means it's a functional failure, it's a flaky, means how we do know the flaky, that we have the history of that test case, that when the test case is failed, when the test case is passed, then we check that is that the test case is a environmental failure or anything. So according to this, actually we give some weighted score to that test case, that it changed the impact score there. Then um, then we have predict the impact and score and rank that, then execute the test case. And this is the circular thing, means every time it's run, it's ingest the test case, and our engine is mature and mature, so we get good result from that. Next page. So in the week one, normally when you deploy, the accuracy is around 85%, but because its initial build are there. If we have more than 200 builds, the accuracy what we get is around 92%, and after thousand of builds, around a quarter later, it's around 96%. After a 6 month, when the mature system, we have a lot of data in our engine, so it's around 98% of accuracy we achieved. Next. Now we can measure the benefit across several dimensions: the test reduction, impact test recall, the response time, trust, and the retrieval scale. Here we the test reduction we achieve around 90 to 95%. The accuracy we already discussed is 95%. The response time of the API. Why it's important? Because we add this API in our CI/CD pipeline. If the API take a lot of time, then the CI/CD pipeline flow also takes a lot of time. That's why we use the Redis to reduce the response time here, and it's sub 2 seconds here. The trust code, this trust code is we have some mechanism that we find out means we get the feedback from the user. We find out the false positive, false negative, that data, and do. And currently in our code base, around 100k plus of test cases are there. So this what we result we discuss here, all are, it's a mature system having 100k of test cases are there where we test it. Next page. This comparison show the operational difference between running everything um, and running a change your subset. Instead of treating all 50k tests equally, we prioritize the test most relevant to the current code change. That translate directly into shorter feedback cycle and significantly lower CI infra consumption. But the real headline is not simply fewer tests. The real benefit is achieving fast confidence here. Next. This is the most important thing everyone is asking. Uh, what if AI miss a test case? This is probably the most important production question. What happens if AI skip a test that could have caught a defect? Our answer is layered safety. Mandatory smoke and critical path test can always run regardless of the recommendation. For risky or uncertain changes, we can automatically lower the threshold. Why lower the threshold? If lower the threshold, that the impact set test set should be higher. Expand the selected set or fall back to the full regression we did. So the principle is simple. The model purpose, the policy governance, and when confidence is low, we test more, not less in that time. Next. We did our early validation in our organization, and we find we have learned a lot of things there. First, as we give the impact for a specific build, means if there is a build number 200, okay, in build number 200 have some changes in authentication services, so we give the build if, and we find the impact for that build if, and we give that. But due to some reason there is some issue in CI/CD pipeline or anything, there is some issue, so we can't run the regression pipeline on the build number 200. Then what happened, there is new build is coming, that is 201. There is some other changes there. So what happened in previously, when our engine is not mature, so we only give the 201 build number impacted. Those build if are present in 201. So we missed all the 200 build number build if. So what happened? It's actually skip a large issue. So we fix that. So what happens if your build 200 is not run and we run directly 201? The smart engine is know that the build is 200 is not run, so it's give the impact of both the builds, the 200 and 201 in that run. So it's not missed anything from our end. As well as if a test case is failed, so in the next time the test case automatically add that if the test case is a functional failure, because the test case can be failed due to the flakiness, the environmental issue. If the test case have some semantic similarities, then if the test case is failure in the environmental, still it add. But if the test case is failed due to functional, it definitely add to the next build. This is actually we learn from that. Then second is the auto detection of the new test case. If a team is writing some test cases in a new dev branch, if write some 10 or 20 test cases, just push it. So in the smart run, the test cases will not run, because if actually impact is finding, then only the test case will run. But we add the capability here that whenever new test is added, it's automatically stored in our database, and it's by default added to the next impact. So the new test case will definitely run that, actually test the stability of the new test cases. Next, actually we have every execution give us the additional information that can improve our future prediction. So persistence, automatic discovery, and control continuous learning are what make the solution sustainable at enterprise scale. Next, if there is one idea I want you to remember, it is that the impact based testing is not simply about running the fear test. It is about running the right test for the right code change using multiple signal and explainable reasoning. When confidence is high, we can isolate feedback. When confidence is low, our safety mechanism automatically broaden the testing. Ultimately, the test smarter, release faster, and stay confident. Thank you, and we are happy to take your question now.
Thank you so much, Srikant and Navneet, for the amazing sessions. We can go ahead and take up the Q&A. So here's the first question. Need to ask, if AI can predict where a change will have the biggest impact, should we still run every test for every release?
No, no.
No, no.
It's so we, as Srikanta mentioned, we always have a fallback mechanism, right? So if we know that like you have under change, let's say you make Java 17 to Java 21 kind of change, that kind of change actually requires or deserves full regression. And also as a fallback mechanism or additional guardrail, we expect when we are working with our internal teams within UKG, we are giving them a recommendation that every third or fourth or every nth run should be a full run because it's AI, right? So we always wanted a human kind of in the loop kind of a system where you run everything so that you don't skip the defects. It's AI; it can give you the false positive or the false results, right? So if AI predicts that impact is huge, so AI won't. So if AI will predict a huge input, it will give you probably 80% of regression rate. But that's where you really want human intelligence in the loop and switch back to the full regression and do the full regression. But that huge changes biggest like for that huge changes going to the system, the probability is maybe less than 5%. Like maybe 95% of the builds have less commit, or maybe 4 or 5 different commits, not like 100. We are trying to solve that specific problem.
Sure. We'll go ahead and take up the next question. Should every iteration be deployed? Do you have any suggestions for impact size of the deployment?
So when we say deployment impacts, like I'm not sure, like are you referring to the to the build deployment, right? So in that case, no, so this tool doesn't govern the impact size of the deployment. We take whatever's going into the build, and based on that we recommend, right? So we don't. So most of the like in today's SaaS world, like teams, like a lot of organizations, they do every iteration is getting deployed. Not all organization, enterprise application organization follow that, but organization like Facebook or like they are doing hundreds of builds getting deployed into the production system probably on a daily basis, right? And that's where they are testing. So each and every commit actually trigger a pipeline, and then it the pipeline actually go and take that code right into the production, right? And that's where it can be where hundreds of different regression workflows are running in parallel. That's where it can save. This tool can save a lot of your compute cost and can the lead time into the feedback.
Another question. How to generate test data customized with enterprise applications?
Okay, I'm not sure that's Shinanda. Do you want to take that? I'm not sure it's
Yes. Yeah.
associated.
Yeah, actually, test data and test case we are not cater here. Actually, already test case those are written by the team. Actually, we pick that in our engine and we predict according to that.
So we don't create new test cases using this tool. We are only taking whatever is there in your regression suite.
Thank you. We'll take up the last question. I think there's some audio issue, Navneet, from your end. We can hear.
Okay.
So next up, it's what happens when an agent discovers a faster way to achieve the goal that bypasses an important business control? Srikant, you would be taking
Yes,
this up?
yes, yes, yes. Agent. Yes, actually, we have the safety mechanism we have, and we have the control. The engineering team have the full control to run the full regression or anything. So whenever we feels that the impact we are getting is not up to the mark, so we definitely go for the full regression or anything like that.
So the ultimate control is with the team. Like they can
Yes.
lower the threshold, they can fall back to the full to that full regression, as well as the system matures, like as the tool is getting trained with your application, the false positive would drop significantly. That's what we've seen in our seeing into our organization. On day one, definitely you won't get all the right results, but as Srikanta mentioned, like probably in 6 months you'll start seeing that your the confidence into that the subset that you're getting would be way above like 98% or before that, like maybe in first quarter or so. That's where we definitely need a human diligence to figure out like whether this impacted test cases is important, or we looking at the code change getting the system. Do we need much more regression even if it's taking more time?
I think that's it for the questions. Thank you so much, Srikant and Navneet, for the amazing session. So we had the great session over here. Test selection that learns from every cycle and the discipline of proving it. You guys really told that it doesn't miss critical defects and trade-off every large suit owner is weighing right now. And just a reminder for all the attendees, all the sessions will be available on our YouTube channel, so you can go and visit them again. Thank you again. Happy testing. Looking forward you for other sessions as well. Thank you, everyone.
Thank you.
Thank you.